me check. And do you remember the talk for next week's, or the title for next week's talk? I guess. Look it up. By Perry Sampson. I think it's.
That's what I thought. Oh, you're okay.
Can I use this for a second?
Thanks. Oh, this is interesting.
Okay, so welcome everyone to MISC. As a reminder, MISC is weekly, Tuesdays at noon. So next week we're going to have Perry Sampson of Department of Climate and Space Science Engineering giving a talk called Quantifying the Impact of a Backchannel on, Quantifying the Impact of a Backchannel in a Large Lecture Course. So that's going to be next week at noon again. So this week, please welcome Sam Carton. He is a PhD student here in the School of Information. He's advised by Xiaojun Mei and Paul Resnick as well. So thanks, Sam, for coming to talk. And yeah.
Thank you. Today I'm going to be talking about the work that I've been doing recently in both designing algorithms and designing evaluation protocols for interpretable machine learning with applications to social computing. Should have been the subtitle of this talk, so that's my bad. I'm going to begin with a kind of introduction to the nascent subfield of machine learning that is interpretable machine learning, and then I'm going to talk about each paper in turn. And then, as is conventional, I'm going to finish off with a bit of an overall conclusion. Before I begin, I want to issue a bit of a content warning. The application that I've been working with is personal attacks in social media and machine learning pertaining to the detection and identification thereof. So some of the slides that I'm going to be presenting are going to include stuff like profanity and slurs and various other kinds of objectionable content. So if you don't want to deal with that, you may want to take off before I hit paper number 1. So, sorry, I should have put that also in my description of this talk. All right. So beginning with a bit of a discussion about the use of machine learning in social computing. Social computing, machine learning is everywhere. It's doing all sorts of stuff. There are a bazillion ways in which it's affecting our experiences on social media. Platforms use machine learning to recommend content. They use it to recommend friends. They use it to detect objectionable stuff. They use it to screen for mental illness, or at least there has been academic work about that. They use it to catch spammers and bots. There's a range of different stakes in play, right? Ranging from low stakes stuff where it doesn't really matter if you get it wrong. It doesn't really matter if I recommend someone who you don't actually know in real life as a friend. Not a big deal. To pretty high stakes stuff. You know, if I'm going to ban you from my platform, that's a fairly high stakes decision, which has the potential to harm people if it's made incorrectly, both false positives and false negatives. As a result, particularly when it comes to these kinds of high-stakes decisions, there's a growing feeling that there is a need for transparency in the application of machine learning to social computing. Can someone close those windows, please? Thanks. These decisions that have a high potential to hurt people arguably kind of need human oversight at some level, right? If you're going to be banning someone from your platform, if you're going to be recommending some kind of intervention, you know, like calling the police on someone who seems like they might be a shooter, you need a human in the loop. You can't be doing that stuff automatically, probably. And then on the other side, there's also kind of an idea that's out there, which is that there's an ethical obligation to provide explanations for these decisions. So you have, your algorithm makes a decision about someone that affects their life, they have a right to understand why that decision was made. And that's a fairly prominent part of the GDPR, the EU regulation that just got, that's getting implemented right now, is to say you have a right to an explanation. Simple algorithms are easy to explain. If you're banning content based on does it have curse words in it, it's easy to explain why you banned a piece of content. It had such and such curse word in it. The same goes for like simple models. So if you're using something like a decision tree, and I'll talk a little bit more about this, it's fairly easy to explain how you arrived at some decision, some algorithmic decision. However, the trend in data science and machine learning is not, is away from these kinds of simple, easy to interpret models. It's toward these very complicated models, neural nets in particular, which have hundreds of thousands of parameters. They work in very complicated nonlinear ways, and they don't necessarily correspond well with it to human intuition. So the point being that this problem of transparency is non-trivial. It's non-trivial to try to explain the behavior of these fashionable, complicated powerful models that are increasingly being used to make decisions about, well, everything, but social media, social computing in particular. Hence the need for model interpretability, which is this kind of burgeoning subfield within machine learning. And it's the idea that we want to understand the logic underlying the decisions made by trained machine learning models. There's a number of ways of kind of breaking down this field, and I'm going to talk about them very briefly, each in turn. So I'm not going to bother enumerating them on this slide. The first breakdown within this field of interpretability is this idea of global interpretability versus local interpretability. Global interpretability is you have a model and you want to understand broad insights about the way that the model is behaving. So you want to know what features tend to boost the model toward one outcome, what features tend to boost it toward the other outcome. A lot of the interest in this particular kind of interpretability is for science. You know, we've trained a model on a big pile of data. What insights can we derive from that model? What is it learned? And can we learn from the model? Another thing people do with this is model verification. Does it make sense? Is it learning things that correspond well with our intuition about this domain? The other kind of interpretability is local interpretability. And that's the idea that you want to understand individual decisions being made by a model. So why did this model make this decision about this person in this context? Why is this person likely to be a school shooter and this person isn't? Why is this person depressed and this person isn't? Why is this person, why should this person be banned and this person not be banned? And the idea there mainly is that you kind of want to be able to troubleshoot these decisions or understand them. So you, as a human overseer, you want to know when the model is right, when it's wrong. To what extent should you be able to take this model's output as a bus? You want to be able to reason about the output of the model. Does that make sense? Okay. And yet another breakdown in the literature is the idea of explaining versus interpreting models. There's a very nice white paper by Cynthia Rudin at Duke from this past year that articulates it in this particular terminology. But basically, it's the idea of, do you train an opaque model and then try to sort of explain it in a retroactive post hoc manner, or do you train models that are intrinsically interpretable in their own right? And there are upsides and downsides to the two approaches. In the explain case, where you're doing these kinds of post hoc analyses, the nice thing about them is that they kind of work on any model that you happen to have. So you can have parallel lines of research where, you know, one line of research is advancing the state of the art. You know, you've got your Google, your BERT model, state of the art. And then you can have a parallel line of research that's working on explaining any arbitrary model that you happen to be working with. You don't need to do extra work to kind of combine the two. You may have heard of LIME. It's a very well cited example of this type of approach. It's the idea that you approximate a complicated nonlinear model with simple linear models in a particular region of feature space. And then you use the coefficients of that linear model to explain the behavior of the complicated nonlinear model. What basically, it's a post hoc analysis, and it can be contrasted to the idea of built-in interpretability, which is a model that, one way or another, you can just look at it and understand how it's functioning. The most common way for this to be the case is just a simple model, logistic regression, where you can look at the coefficients and understand how it's behaving. The more complicated way of doing this is to place interpretability constraints on your model. You force it to be interpretable, and the most common way of doing that is with this idea of attention. So you force the model to be explicit about what parts of the input it's attending to. So is this person depressed? Well, this particular sentence and maybe this particular sentence over here indicate that they are. That's kind of what's going on with the idea of attention. There's a variety of different types of explanations that people have experimented with producing. The most common of which is this idea of feature selection, identifying what parts of the input led to the output. By far the most common way for people to approach the problem. But other things have been tried, including natural language. Can you generate text that sort of explains in a verbal way why the decision was made? Explanatory examples are another popular thing for people to kind of experiment with. So this person is depressed because they're very similar in their profile to this other person who did turn out to be depressed, or vice versa. That's the logic kind of being employed there. Another thing people use sometimes is rules. So can you take a complicated neural net and sort of approximate it with a set of logical rules, which is much more understandable? And there's been actually a surprisingly large amount of work kind of in that area. So the point being that it's all of this is very up in the air. There's not a lot of consensus over what constitutes the right way to do interpretability. That's really the point that I'm trying to make by presenting all this information to you, is that it's a very wide open field. As you can imagine, the type of data you're working with matters. Different kinds of explanations are going to lend themselves better or worse to different types of data: text, images, miscellaneous numerical data. And then there's also a difference between engineered features and learned features. So in kind of an older machine learning paradigm, you're gonna handcraft a whole bunch of features about your input domain, and then you're going to throw those into a fairly simple model. And those kinds of things are fairly easy to explain. You can say, I think this person is depressed because their use of words that have been manually identified as associated with depression is higher. These kinds of named features. As opposed to the more trendy current approach in machine learning, which is not even to bother. You just allow the models to develop whatever representation they need to perform well, and then you work with that. But it's harder to explain. Finally, and perhaps most importantly, is the idea of evaluation, which is really the question of what is interpretability, and what does it mean for an explanation to be effective? So what is it that we're trying to accomplish when we explain the output of a predictive model, and what makes one explanation better than another, and how do we gauge that in a way that's cost efficient, and so on and so forth. There's a nice paper by Finale Doshidelis at Harvard, where she breaks it down into 3 types of explanations, 3 basic types, one of which is application grounded. It's the idea that you have a task that you're trying to perform, you get actual humans to do it, and you say, are they doing better with interpretability or without? It's kind of the obvious thing, sort of expensive, can't do it all the time, you can't do it quickly or cheaply, but it's really the only way to know if interpretability is accomplishing what you want it to accomplish in the context that you're working in. She also identifies human-grounded, which is where you have humans still, but they're working on some kind of proxy task that's a little bit different from the actual domain in which that model is intended to be deployed. A very common thing to do kind of under that category is ask people how much they like the model they're working with. Do you trust this model? Do you like it? Did you think it was helpful? Did you think the explanations were helpful? And as you can imagine, there's some value to that, but it doesn't necessarily correspond all that well with performance. And then finally, there's functionally grounded evaluations, where the There's no humans involved. You're just working with some kind of proxy task or proxy data. And the most common way to do that type of evaluation is to argue that a simpler explanation is better. So if you're including less information, that's a better explanation. And you can sort of imagine there might be some problems with that logic. You know, a simpler explanation is not necessarily a more complete explanation or more understandable. Please, by the way, ask questions if I'm being too jargony. You know, I prefer to be interrupted than to have what I'm saying, you know, sort of not say it, or any other reason. Okay, so moving forward, this talk is going to be about two papers, one of which I sent to a conference last year, one of which is currently in submission. The first paper is an interpretability algorithm, and the second paper is an experimental protocol for evaluating that algorithm as well as some other reasonable baselines. So I'm going to kind of, you know, it's a two-part talk. I'm talking about both algorithms and evaluation. All right. Got a dead crowd. That's all right. Okay. So paper one, interpretable model. The idea here, and this is where the objectionable content begins. So again, I apologize. Is that we want to look at comments derived from social media, and we want to identify whether they have personal attacks in them. And beyond that, we want to also identify the tokens in each comment that are parts of personal attacks. And so it's both a prediction task and an explanation task. We're trying to predict, yes, no, does this comment have any personal attacks? And then the explanation is trying to identify all the objectionable content in any comment. And you can see here, I've got an example of a deeply objectionable comment with stuff that the model has identified as objectionable, and then sort of less objectionable comment, and the one token that the model identified as potentially problematic. I'm working with a data set which is very neat. It was presented at WWW in 2017. It's 100,000 Wikipedia revision comments that have been labeled for aggression, toxicity, and the presence of personal attacks. Very high quality. And they used Crowdflower to collect this data. And importantly, they had roughly 10 annotators per item, which is nice because it means that you have a continuous target value to work with for each item. So some comments are more of a 0.3, you know, they're a little objectionable. Maybe 3 out of 10 people thought this was a toxic comment. And some comments are 1.9. You know, everyone can agree that this is a bad comment. As a validation tool, I got a bunch of UMich undergrads to collect, to label comments at the token level. So I had a bunch of undergrads identify personal attacks within the text of comments. I don't use that for training, but I do use it to sort of validate my algorithm. So basically the idea is that I want to be catching as many personal attacks as possible, even though I don't have this kind of token-wise data to train on. The model that I use, it's a neural net. It's an attention model, as I kind of touched on earlier. The idea behind most attention models is that you have one layer that is producing a weight on each input, and then you have another layer that's making a prediction from the weighted input. That's the typical setup. Generally speaking, these things are optimized to do two things. They want to both be accurate, and they want to be sparse. They want to attend to as little as possible. That's the typical attention setting. So in my little toy example here, the attention layer has decided that the tokens huge jerk are important, and the tokens URA are not important. And so it exposes those and hides those, and then the prediction layer makes, we can only assume, an accurate prediction from those two exposed tokens. Yeah?
I guess just a question about attention models. So do you have to train those two layers separately?
So the cool thing about neural nets is that you can train them in tandem. The attention layer feeds directly into the prediction layer. It's all differentiable. And so therefore, that you can use the same objective function to perform gradient descent on the whole model.
But do you need to have attention, like what you should pay attention to labeled?
No,
separately?
no. So you can have a global objective function for the whole model that penalizes mistakes, as one does in machine learning, and then also penalizes amount attended to. And you can kind of count on the gradient descent algorithm to find some reasonably optimal balance between those two objectives, where it's throwing away as much data as possible while still remaining accurate. Yep.
So does the attention layer require a context-specific dictionary, like a dictionary of insulty words?
No, it sort of learns more. It learns to kind of do that automatically. That's what's cool. So the attention layer produces a weight on each input. So it has a sequence output. As you can sort of see, it's producing one output per word. And then the prediction layer is taking that as input and producing a single output, which is a prediction about the whole comment. And like I said, you can train them together with this kind of joint objective to get this kind of neat result. Okay? So what I add to this basic framework, and we're getting a little into the weeds here, so bear with me, is the idea of not just having one predictive layer, but two. And the first predictive layer, as in this sort of basic framework, looks at the attended to content. The second predictive layer looks at the stuff that was left out of the attention. You can think of it as kind of the inverse attention, the anti-attention. And what I argue with the design of this model is that not only do you want the stuff that's highlighted to be sufficient for good prediction, but you also want the stuff that is left out to be insufficient for good prediction. So within the context of this particular task, what I'm saying is that not only do we want enough personal attacks to be attended to make an accurate prediction, but we don't want to leave any personal attacks out of the attention. And that's not necessarily something that's guaranteed by the kind of basic attention mechanism. Because going back, the two things that we're optimizing for are accuracy and minimal attention use. I really should have illustrated it, but you can kind of imagine that if you had two personal attacks in here, you are a huge jerk, go to hell. You would only need to see one of those to know that this comment had at least one personal attack in it, right? And so what this kind of tries to guarantee is that all of that objectionable stuff will be left in the attention mask. Yes?
How would those comments be chunked out, right? Like if you have an entire sentence that has like 3 offensive phrases in it.
The model will decide.
Okay.
The model will decide what tokens it needs to attend to make a good prediction, as well as what tokens it needs to attend to in order to prevent the adversarial predictor from making a good prediction. And so that kind of happens almost automatically in the training process as a result of the objective function. Yes?
So, since it's a personal attack,
Yep.
right? I know for this example you're missing on you, but let's say someone just say you jerk, that's not essentially a personal attack.
Yep.
So the model will automatically pick that personal
So
context as well.
So this is actually a little misleading, because what would probably happen here is that my model would probably end up attending to everything. And the reason it would probably end up attending to everything is that if you see the phrase "you are a" and then nothing, you can make a pretty good guess that there's a personal attack that's about to happen. You may not be able to see the actual attack, but you're on social media, someone says "you are a blank," that's a pretty clear signal that there's a personal attack that's going to happen here. So what would probably happen in this little toy example is that the addition of this adversarial layer would make the model include U and R and A in the regular attention. It would shift it out of the inverse attention into the regular attention. So this is all about what the predictive layer can and cannot guess will be the case. It's about allowing the primary predictive layer to make a good prediction and preventing the adversarial predictive layer from making a good prediction, and having them kind of fight each other over what gets attended to and what gets left out of the attention. That's the central mechanism here. So there's another part to this as well, which is a little bit less sexy. But it's the idea of manipulating the bias term of the model. And what this basically does is it says that the model is going to have a prior belief that any comment is going to be benign. So given zero information about a comment, the model is just going to default to saying it's fine. Meaning that if the attention mask includes nothing, the model is going to guess, in this case, 0, which is indicative of no personal attacks. And this turns out to be kind of an important point, because what it basically does is it explicitly chooses a semantic meaning for the highlighted. By doing this, what we're saying is that anything that is highlighted in a comment should be all of the stuff that distinguishes that comment from a benign comment. That's what that does for us. So it's just another part of kind of computational machinery that makes it easier for us to get something that is a little bit more reliable in terms of what it means. So take it all together, and you end up with a model that is trying to do a few different things all at once, and is able to do an okay job of kind of balancing them. It's trying to make accurate predictions. It's trying to use as little attention as possible, but it's also trying to include all personal attacks in the attention. So you can see this example that I showed earlier, it's trying to sort of identify everything bad within this comment, to the limit of its ability to do so. And it does a pretty good job. You know, it gets, you should get a life, which is not an obvious insult from the words that are being used. But it's not amazing, so it doesn't catch, you're an extremely self-centered. So it's not miraculous, but it does an okay job in this particular example. Okay. I know this is awful. I always hate it when people make slides like this. There's a couple of fairly simple takeaways for the results of this, which is basically that the adversarial predictor thing improves the recall over the sort of basic setup, and the bias term manipulation improves the precision. Those are the two basic takeaways. The other kind of takeaway is that the final performance, the performance that the full model achieves, is fairly close to the extent to which any two humans are likely to agree with each other. So we're kind of beginning to hit the upper limit of like how well we can really do even in theory, just because identifying tokens that are parts of personal attacks is a fairly subjective thing, and different people are going to have different preferences. You know, like you in huge jerk is huge part of the personal attack, or is it really just jerk? Different people will kind of do different things, and it makes it kind of a noisy problem to try to solve. Okay, so wrapping up this chunk of the talk, we have this idea of explanation by attention, which is that you're highlighting the stuff that the model looked at as a way of explaining why it made the decision that it made. We've got this idea of adversarial attention, which tries to put all of the predictive stuff, all of the predictive signal, in this case all of the personal attacks, in that highlighted stuff that's being attended to. And we have this idea of bias term manipulation, which is setting a prior on model behavior, and effectively it chooses what it is that your explanations mean. It sets a meaning for them by way of contrast. You're saying what you're really doing, what I'm really doing by doing this is I'm saying an explanation of why is really an explanation of why not. Why not the prior? Why not the default belief? If I were you at this point, I would be thinking, why? Why do all this? What's the point? Who cares? Great. You're able to identify the toxic stuff within comments, but you know, why? And that's kind of the question that I try to answer in this next paper, which is about evaluating interpretability. So going back to, briefly, the evaluation in this paper, this is a functionally grounded evaluation. It's a proxy. There are humans involved, but they're not actually using the system to try to perform some task. It's a retroactive evaluation. So moving forward into this next paper, we kind of consider an application-oriented evaluation of this model and other kind of reasonable baseline models. So what we do is we sit a bunch of mechanical Turk people down in front of comments drawn from this data set, and we ask them, how toxic do you think this comment is? And in particular, what percentage of people are liable to find this comment toxic? And the main research question we ask is, do explanations help people do that? Particularly in the presence of a prediction from an unreliable model. We've got through the sort of basic research questions. What is the impact of having a model prediction in the first place? And then, given that you have a model prediction, what is the impact of explaining it? And then, does the type of explanation impact any of these variables? So if you generate this attention mask with a different procedure, how does that affect the situation? So you can see here an example of the kind of stuff that some of these subjects would be working with. You've got a comment. It's very toxic. The model has made a prediction. We ask the subject what their prediction is, given those pieces of information that we've offered to them. It's a two-part experimental design. In phase one, we're collecting ground truth toxicity values. So we basically ask for each comment a bunch of Turkers, do you find this toxic? And we aggregate that into a score for each comment. So each comment, either a small minority of people found it toxic, or a minority, or a majority, or a large majority. So we have quartiles. That's a subjective task, obviously, but then in phase two, what we're doing is we're asking subjects to predict the outcome of phase one. So what percentage of Turkers do you think found this comment toxic? And we use the result of phase one as the ground truth for phase two. We do all this on Mechanical Turk, and we've got about 300 subjects. Comment selection, we sample, each person looked at about 50 comments, 48 comments. We sampled them in a stratified manner from that data set that I mentioned earlier. Don't need to get into these details too much. The takeaway is that we have a range of different true toxicity values that each person looked at. So they were looking at some stuff that was really benign and some stuff that was really toxic. And we have a range of model accuracies. So we were looking at some comment, each person was looking at some comments for which the model is accurate on that comment and some comments for which the model is inaccurate. And in particular, we oversampled model errors. So that means that subjects were working with an artificially bad version of this predictive model. That's kind of a key thing to keep in mind here as I launch it, as I move into talking about phase two and then the results. It's a bad model, worse than a real model would be in real life. So in step one, as I said, we're collecting this ground truth. We ask each person to read the comment and then decide whether they find that comment very toxic, toxic, neutral, or healthy. And we took this questionnaire from the original dataset paper because we wanted to kind of recreate those results in a more statistically robust way. So we wanted to make sure that our ground truth was really valid as a ground truth. That's why we even bothered doing phase one in the first place. Phase two, we've got another group of subjects trying to predict the outcome of phase one, as I said. We've got two treatments, one of which is the presence of this model prediction, and one of which is the presence of this highlighter. And we have about 11 subjects per condition. We've also got two extension conditions where we experiment with a couple different variants of the highlighting explanation algorithm that I described in the first paper. One of which is a partial variant, where we reduce each set of highlights to just the most toxic phrase. And one of which is a keyword method, where we essentially create a dictionary of toxic words, and we only highlight those. And these are examples. So here, it kind of gets, this whole phrase. There, go F yourselves. low likely. When we do the partial variant, we're reducing this whole thing to just the thing that the model thought was the most toxic. Personally, I kind of disagree with this. I think this phrase is more toxic than this phrase. But this is what the model thought was the most indicative of the toxic outcome. And then when we do the keyword highlighting, we're just looking at individual words that are globally found to be toxic. And it gets kind of different stuff, right? So this particular word is found to be indicative of a toxic outcome. But it's not highlighted by the model in the full variant. And so what we're trying to do with the partial highlighting variant is we're trying to answer the question, do you really need to highlight all the toxic stuff? Is that actually necessary? Or is it okay to just get kind of the minimal, sufficient toxic content and present that to the human and let them work with that? And then what we're asking with this keyword highlighting method is, do we really need to do this complicated neural approach, or can we work with a much simpler kind of dictionary-based approach to doing this highlighting? So as a recap, task, predict, parametric toxicity. There are 6 conditions representing variants of having the prediction, having the explanation, and then the 2 different types of variant explanation. We're interested in how accurate people are with respect to the grammar truth, how fast they are, and the extent to which they agree with the model. Are they more or less likely to agree with the model when there is an explanation for the model output? And again, our research questions are basically, what do predictions do? What do explanations do? What do the explanation variants do? Another terrible slide, sorry. And it's even cut off there, great. What we basically find is that explanations don't really do much in terms of accuracy and agreement. People are no more accurate with explanations than without. They are no more or less likely to agree with the model with explanations than without, or at least not to any extent that we can statistically discern. We find that they tend to believe the model when it makes a prediction. You know, people are kind of gullible, or they're pliable. We find that the addition of a prediction slows people down, which kind of makes sense if you think about it. So you're reading a comment, and then you have to kind of read this prediction, and then you kind of have to like reconcile the prediction with your impression of the comment. Sort of makes sense. And then we also find that that speed penalty is mitigated by the explanations, which is nice. So people are doing about 7 seconds per comment without any algorithmic assistance. That rises to about 10 with a prediction, and then it falls back down to about 7 with explanations. So that's an outcome. But this is mostly negative. What we're really finding here is that explanations don't help as much as we would like. And in fact, we actually find that the partial explanation variant actually hurts performance. It hurts recall. And that's another outcome. So what does all this mean? What's the implication? What it means is that explanations don't help as much as we would like them to, and in some cases they can actually hurt. And that's a negative outcome, and no one ever likes a negative outcome in science, but it's kind of an interesting negative because the interpretability literature has this implicit assumption that explanations help, or at least don't hurt. This idea of transparency is kind of offered as a panacea to all the problems that are associated with the use of machine learning in these high-stakes tasks. And our findings kind of complicate that story. They say, well, no, not really, not necessarily, not in this context. And a bad explanation can actually suppress critical thinking. It can make people less good at troubleshooting a model, less likely to apply their own reasoning, more likely to be fooled by bad reasoning. So what it really does is that it calls for more work. It calls for work on new kinds of algorithms to explain model predictions, and it calls for more work on understanding these sort of human factors. Another important question to ask about this work is this externally valid? We are interested in this kind of semi-automated moderation task, moderation setting. But what we really work with is this task of toxicity prediction, and there are differences. In moderation, you have trained moderators. They're applying a well-defined, more or less, set of community standards. In our setting, we're using untrained mechanical Turk people, and they are applying this kind of loosely defined question of, is this toxic, or are people likely to find this toxic? And so there's this question of, is this a reasonable proxy? And we've gotten some criticism from reviewers about this before. We argue that it is. We argue that even in a moderation setting with a well-defined set of standards that you're trying to apply, there's still going to be a lot of subjectivity. One moderator looking at someone is going to say they're trolling. Another moderator is going to read the text differently and decide that they are. So ultimately, a lot of these decisions are going to come down to basically, are the members of this community that I'm responsible for protecting going to find this objectionable, or are they not? So we would argue that this is a proxy. It's a simple proxy. It's not the same as what we're trying to study, but we're arguing that it's close enough for our results to be valid and for the implications to kind of carry over to the actual moderation setting. Okay, we're close to being finished here. I'm just going to give a few broad strokes, conclusory thoughts about these two papers, and then I'll finish up and open up the floor for questions. So I presented one paper that was about an interpretable algorithm. I presented another paper that was about an evaluation protocol for explaining, for evaluating explanations for a text classifier. In the future, what I intend to work on, what I am working on, is both new algorithms. In particular, I'm working with this idea of explanation by example, and more experimentation with hybrid human-AI systems, more experiments to understand how best to integrate some human and AI intelligence. One really big question is this question of training. Explanations may not help untrained Turkers make better decisions, but what if you had a training phase where they could sort of develop a mental model of what it is that the model is doing and sort of learn how to integrate their own reasoning with the model? And would explanations help or hurt with that process? Would they make it faster? Would they make it more effective? Something we didn't touch on at all in this paper. And then another important issue, I think, is explainability versus interpretability. I think there's going to be a reckoning in the interpretability literature over this issue and what is kind of the most fruitful way forward for this particular subfield. So that's all I've got. Here's just, again, the outline of the talk, and kind of what I think is the core contribution I'm making is the ability to do this. I'm happy to take any questions.
So, okay, I think we have 9 minutes for questions, so I'll answer the first one. So actually first, just a kind of factual question. So you talked about how the GDPR includes a right to explanation. So without knowing the specifics of that, what kind of explanation is required? Like, could you just say, oh, well, we have a deep neural network that said this is...
So that's part of that's controversial. The language in the law calls for an explanation without specifying, because no one knows what is really a reasonable explanation for automated decision making.
Okay, so on that note, I'm curious what you think is a reasonable level of explanation. So, because I'm wondering in particular, let's say that a system that does detect toxic comments is deployed. Let's say it's at, I don't know, the New York Times comment section or something like that. And I submit a comment, I can see that it got rejected, I can see why. It seems like it would also just be really easy to say the exact same thing in a way that circumvents.
Yeah, it's tough. The considerations are different for what you present to the moderator versus what you present to the subject. You don't want to give them information with which to game the system. So I would say I don't have a really good answer for that. I would think you would want to probably do something in between this level of detail and nothing.
Question for you. So, for one, I enjoyed the talk. Thank you. This is an interesting work. So paper 2, it sort of interested me that you found that basically that the workers really just defaulted to whatever the model was talking about.
Well, I would say they defaulted to it. I would say they leaned toward it.
So am I correct in thinking that it's almost like if there was more red marks of saying here's why it might be toxic, they basically accepted that? If they weren't toxic, or if it skipped them, or is it, I guess it's both?
I've got a bar chart that I didn't include in this talk, which kind of which visualizes these numbers by the true toxicity value.
So it wasn't that they were meaningfully, like, they weren't thinking it was toxic when it wasn't, so it wasn't consistent bias, it was just...
My read on the situation is that people tend to believe the prediction when it's in front of them. They tend to believe the model, and if I recall correctly, there wasn't much difference in that rate of belief from condition to condition.
It's interesting, because that made me think almost sort of like our legal system, like, it would almost be the idea if you only had a prosecutor, it's only presenting, here's why it's bad. And I wondered how that might change if it's like, here's a model and here are the reasons why we think this is toxic. Here's a different model, like for instance, your earlier work that looked at a sort of, what do you call it, the opposite view. Basically, it's like, here's why we actually think this comment is fine. And then they have to choose between them.
It's a valid point. And there's a difference from domain to domain. So this is a decision problem. If you think about personal attacks, whether a comment has personal attacks has this kind of logical property of no personal attacks. A 0 stems from a lack of personal attacks, if you see what I'm saying. But that doesn't necessarily hold true for something like recidivism. For recidivism, there are going to be some features of an inmate that are positively predictive of, yes, they are going to reoffend, and there are going to be some features that are predictive of, no, they're not going to reoffend. So there isn't this kind of flat semantic logical structure to that. So you have to do something a little bit different. So my answer to that is that it's going to vary from domain to domain, and I would need to be a little bit clever in figuring out how to adapt what I'm doing here to a different domain.
So there's, so I'm not a machine learning person, so I want to get your perspective on this. So a while ago there was an article, I think in Wired, essentially arguing that just training machine learning models on huge amounts of data might not be enough. You need to have some way of kind of manually giving a model some base level of knowledge or some base. When I say structure, I don't mean like the structure of a neural network, but I mean like the structure of, I don't know, what it should. Well, you have to give it some semantic knowledge, I guess. I don't know. Good. So I'm wondering, I guess in part, what, if you think that's true, and what the link between that and interpretable models is, because it seems like a model would need to be interpretable to be kind of manually tunable by people to say like, this is what I want it to.
Yeah, so there's this movement called the FAT movement, F-A-T, Fair, Accountable, and Transparent Machine Learning. And what you mentioned is more kind of along the lines of like fair machine learning. It's the idea that a machine learning model should not, for instance, if you've got a recidivism prediction model, it should not be doing wildly different things for African American people than for Latino people or for white people. And that is behavior that you have to actually kind of write into the model. It won't necessarily develop to be unbiased by itself. So there's a whole sort of field of fair machine learning at this point. I would say that fairness and transparency are related. Like, transparency features will help expose the bias of a model. But they are, I think, ultimately things that kind of can be developed in parallel. So you're going to have this procedure for making your model fair, and then you're going to have this procedure for exposing the internal logic of the model, and then maybe you can use that to check whether the fairness thing actually worked properly. So I'd say related, but not exactly identical. All right, I guess that's it. Thanks for showing up. Appreciate it.